Okay, guys, as promised, limits and continuity. You guys already know what continuity is, and so let's go ahead and let's just sort of look through that. Continuity basically is, the sort of layman's or common man's understanding is it's basically a graph that you can graph without picking up your pencil. Okay. And so basically a discontinuity, a place where the function is not continuous, is a place where you have to pick up your pencil. Okay? Here would be one type of discontinuity. This would be another. And of course here at x is equal to 4 is a third type of discontinuity. Okay? Now, this right here, okay, is what we oftentimes call a hole. So at x is equal to 2, the type of discontinuity at x is equal to -2, it's a hole, or what we used to call alternatively a removable, okay, discontinuity, okay? And I probably misspelled that, but whatever. Now, here at x is equal to 1, there is a different type of discontinuity. Because it's not just as if somebody came up and sort of plucked a point out of the curve. And so forth, it's not a hole, it's not removable, it's not as if somebody removed a point. It actually jumps. I mean, it comes down if you're going from left to right in terms of x. It comes up, and then it comes down, and then it jumps up to y is equal to 4, okay? That is what we call a jump discontinuity, okay? Now over here at x is equal to 4, we have a third type of discontinuity. Okay, it's another place where you have to pick up your pencil. But those two parts of the graph, it doesn't jump. This goes on forever and ever and ever and ever and ever, all the way down to -infinity. And on the opposite side, as you're coming towards x is equal to 4, it goes up to +infinity. This is what's called an asymptotic discontinuity or an infinite discontinuity for, obvious reasons. So we have three different types of discontinuity that we've discussed in the past, okay? And all of that sort of fit underneath our, Algebra 2 and Precal definition of continuity. It is a function whose graph has no jumps, breaks, or gaps. So continuity is no jumps, breaks, or gaps. Discontinuity is a jump, a break, or a gap, okay? So you already know that. And we talked about different types of discontinuity. Obviously, the ones that we are most familiar with are the ones dealing with rational functions, both the removable and the infinite. But we discussed when we talked about piecewise functions, the jump discontinuities. We haven't really gotten into greatest integer functions because I don't find them to be all that helpful and they're kind of annoying. But the only thing that we need to do now is take our knowledge of limits and go from an Algebra 2 and Precal definition of continuity to a more rigorous and robust calculus definition of continuity. And that's what we're going to do, okay? So our calc definition of continuity has to do with knowing limits, okay? And it has basically three aspects of it, okay? If you're talking about a function f of x, okay, you need to know that the limit as x approaches some number a of f of x is equal to some finite number, okay? Now, you also need to know that f of a is equal to, that basically, I mean, you don't have to know what the value is. Let's just say that it exists. I mean, that's basically all you need to know. You need to know that the limit exists. You need to know that the function value at that same input value, at a, exists. So you need to know that the limit exists, the function exists, and thirdly, that those are the same value. Okay? So that's the 1, 2, 3 of the definition of continuity. Okay? And if you're ever asked a question about continuity in a calculus context, and you come to the conclusion that the function is not continuous, you have to basically explain yourself or justify your answer using this definition, okay? So if we go back to the picture that we're given here, why might we say that this right here at x is equal to -2 is discontinuous? Well, it's not because the limit doesn't exist. At x is equal to -2, the limit certainly does exist, okay? And it's not that the function value doesn't exist. We see it up here at y is equal to 5, or f of x is equal to 5, okay? So the function value exists. The function value is 5. The limit exists. The limit's 3. That third part of the definition fails. This is a discontinuity because the limit as x approaches a of f of x is not equal to f of a, okay? Now, at 1, at 1, we don't even get to that third stage of the definition, okay? Because the thing is that the limit as x approaches 1 of f of x does not exist. And you know that, and you can show that by showing the one-sided limit, okay? You can show the one-sided limit. So the limit as x approaches 1 from the left, coming down here from the negative side, is -3. And coming from the right, from the positive side, is +4. -3 is obviously not equal to 4. The limit is not the same from both sides, and therefore the limit as such at x as x approaches 1 of f of x does not exist. And therefore it fails the first part of the definition, the first of those 3 parts. Now, on number 4, the limit doesn't exist, but let's pretend that the limit does exist and that it's -infinity or something like that. You could say that the limit doesn't approach a finite number, but it's actually even easier on this one just to say that f of 4 does not exist. And if the function value does not exist, then that fails the second aspect. So in order for it to be discontinuous, it can fail one or more, and it could fail any one of the aspects, any one of the 3 parts of the definition of continuity, okay? So that is basically how we take the Algebra 2 concept of continuity and make it a little bit more robust with our understanding of limits, okay? But if you're asked a question on the AP exam, which you most likely will be, and oftentimes they don't waste free response questions in dealing with continuity, though if it's, they could, if it's, a really, really small part of it. Most often, though, you wind up getting it in the multiple choice section, and it winds up being, and your teacher will go over those questions as you go forward. Now, the concept of continuity is really not all that impressive. I mean, you kind of go, okay, great, I already knew what continuity and discontinuity was. Now I simply know how it's talked about in a calculus framework. What happens is it doesn't become a really useful tool until such time as you fold in other higher level calculus concepts along with it, and then it becomes, in concert with those other concepts, a much more robust tool, okay? But for right now, what I want to do is I actually want to deal with the variety of questions that they can ask you on, your teacher can ask you on a test, they're going to ask you in a textbook and stuff like that, okay? So if we have f of x is equal to x minus 4 over root x minus 2, and I want to evaluate that at x minus 4, okay? Now, is that continuous? Well, it's obviously not going to be continuous. I go ahead and plug it in, the function value doesn't even exist there, right? So right off the bat, I know that the function value doesn't exist there, but, the limit does exist there, because we can actually say, well, the limit as x approaches 4 of x minus 4 and root x minus 2, it can become, when you force factor the numerator, right? Now, I like force factoring rather than dealing with multiplying by the conjugate. Boom, boom, right? And so the limit here is 4. Now, this is very much in line with the way that we used to deal with graphing rational functions that had removable discontinuities, as this one does as well here at x is equal to 4. And what happened is once we moved from here and factored and canceled, we recognized that there was another function, g of x, that was identical to the original function, except that one point of discontinuity, okay? So if they were to give you a function like this, yes, the mythic they, if they were to give you one like this, and it said, okay, well, why don't you give me a formula for a function that is continuous at the indicated point and is similar in shape, okay? Or, you know, give me one that is almost identical. I mean, I don't know how exactly you would describe it, but basically this function would have identical shape to this function, except for this one, okay? And you remember what this looks like, right? All that is the radical function moved up to, and so it's, you know, that, right? So that's g of x. In order for it to be f of x, you would just have to add a little hole right there at x is equal to 4, okay? So the difference between f of x and g of x is really just that removable discontinuity. So if they said, you know, make f of x into a continuous function, that would be a little bit different, but how would you take f of x, the given function, and make it a continuous function? Well, you would have to plug the hole, right? And the only way to really do that is to do it by piecewise. So you would say, well, y equals x minus 4 over root x minus 2 when x is not equal to 4, okay? And then when x is equal to 4, we're going to go ahead and plug the hole, meaning what would the value have been if it had been g of x rather than f of x, if it had been this with the hole plugged? Well, you just plug it into g of x, and you're going to get root 4 plus 2, or 4, okay? So oftentimes, if you're given a function that has a discontinuity, like a removable discontinuity, a question that can be asked about that is, how would you remedy that discontinuity, i.e., how would you plug the hole? Okay, and so that pops up every once in a while, and it's actually rather straightforward, and you guys that should kind of make sense, because that's only one step beyond what we've actually done in the past, right? What we've done in the past for functions like that, that are rational functions or rational-ish functions, is to identify that point of discontinuity and plot it on the curve as you're sketching the curve, right? The only difference here is you're identifying where that is so that you can set it up into a piecewise function and plug the hole. So one step removed from what we've done in the past. Something else that actually can be asked, and they love doing this type of stuff, it's all over in all of the textbooks when it comes to discontinuity and continuity. For what value of a is this piecewise function continuous? So basically all this is saying is find a value of a that ensures that these two pieces of a piecewise function don't come to a jump. They actually meet, okay? And so all you really have to do is the place where they potentially meet is at x is equal to 3. And so you get 3 squared minus 1 is equal to what? And then you have 2a times 3 is equal to what? This winds up being 8. This winds up being 6a. So a is equal to 4/3. Okay? So if a is equal to 4/3, that ensures that this linear, which becomes 8/3 x, it ensures that this linear meets up with that curve right there and creates and creates sort of a fusion there at x is equal to 3, such that you no longer have a discontinuity, but you then have a continuity there. I'm going to go ahead and stop the video here since it's about at 15 minutes, and I'll go ahead and do a second one on continuity. But I thought it was going to be useful to go ahead and at least do a little bit of background and sort of draw on that prior knowledge, since I know that we kind of went over a whole lot of that, especially in the context of rational functions in the past, and of course also with trig functions and whatnot. Yeah, okay, we'll go ahead and do another video.